In this video, I wanted to talk about bending stress and then also deflection. So with bending stress, we have a formula, which is that the bending stress equals the bending moment times this y, which is the distance between the neutral axis and the point of interest. And then we divide that all by I, which is the area moment of inertia. So in the PE handbook, if you search for area moment of inertia, there's going to be a table with a whole bunch of different shapes and cross sections, and it'll give you the formula for I for various different shapes. For the bending moment, it depends on how the beam is loaded, but you might end up needing to draw a bending or a shear moment diagram to find what the maximum is. But yeah, this is the main equation. And then for deflection, if you just search for deflection in the PE handbook, you'll have a table that'll have a whole bunch of beams that are loaded in different ways, and it'll tell you the equation for the maximum deflection. So I have this example problem here that says a 6-foot-long cantilevered beam is loaded at its free end with a 300-pound downward force. The beam has a rectangular cross-section that is 3 inches wide and 6 inches tall. It is made of steel with a Young's modulus of 29,000 ksi. And we are asked to find the maximum bending stress and then find the maximum vertical deflection. So we have a beam here that is 6 feet wide or long, and we're loaded here with 300 pounds. So since this is a cantilever beam, I know my maximum bending moment is going to be whatever my reaction moment is here. So if we set the sum of the moments about this point here equal to 0, we're going to get, in the negative direction, we have 300 pounds times 6 feet. And then we're going to have a positive reaction moment there. So there's just going to be plus m. So my m is going to be 1,800 foot-pounds. And again, since this is a cantilever beam, I know that's my maximum bending moment. If this was supported or loaded in a different way, that's not necessarily true. And so you would have to draw a bending moment, a shear moment diagram. And on your moment diagram, that's where you'd get your maximum bending moment from. But now, I'm going to want to go ahead, let me write this equation. So I want to go ahead and solve for I. And in the PE handbook, you can find this just by searching for area moment of inertia. And then if we look at the rectangular cross-section, we know that I is 1/12 times the base times the height cubed. So that's going to come to 1/12 times 3 inches times 6 inches cubed. So my I is going to be 54, and that is in inches to the 4th. And then now, what's my y value? Well, so if we look at the cross-section of the beam here, we know that the neutral axis is just going to run through the centroid, which for this case is going to be the middle. And if we want the maximum bending moment, again, this y is the distance between the neutral axis and the point of interest, so either up or down. And since we want the maximum, we know that this is going to be maximum when our y is all the way out here. So the y we're going to use is 3 inches, which is half of the 6 there. So we should have enough information to solve this now. So the bending stress is going to equal to 1,800 foot-pounds. I'm going to go ahead and convert this feet to inches, since everything else is in inches. So times 12 inches per foot times my y, which is 3 inches, then divided by 54, which is to the fourth. So everything should cancel out here. My feet cancel out. 2 of my inches are going to cancel. I'm left with pounds per square inch, which is what I want for stress. So it's going to come out to be 1,200 psi. So that's our answer to A. Our maximum bending stress is 1,200 psi. And now we're going to find the maximum deflection. So if we search for deflection in the PE handbook, and then we find a cantilever beam with a load concentrated at the free end, we can find the y, which is our vertical deflection, equals P, which is the load at the free end, times the length of the beam cubed, divided by 3 times our Young's modulus, times our area moment of inertia. It's very handy that the PE handbook has these deflection equations, because it can take a very long time to solve this, because it's a differential equation you have to solve. So it can take quite a while to solve this type of problem by hand. But thankfully in the PE handbook, everything that you'll need on the test is going to be in a table of deflection equations. And there's little diagrams on there that'll show you how it's loaded, and then also kind of a verbal description of it as well to help. So my maximum deflection in the vertical direction can be my load, which is 300 pounds, times the length cubed. I'm going to go ahead and convert this to inches. So 72 inches cubed times 3, or divided by 3, times my Young's modulus, which was 29,000. I'll do times 10 to the 3 pounds per inch squared. And then we're going to multiply that by 54 inches to the fourth. So let's go ahead and make sure everything cancels. So our pounds are going to cancel. And then we're just left with 1 inch up top, which is what we want. So that's going to come to 0.024 inches. This type of question is pretty easy on the PE because everything is in a table. Just make sure you know your keywords. So for solving for your area moment of inertia, that's what you're going to search for, is area moment of inertia. To get your deflection equation, just search for deflection. And then you can get this equation here by searching for bending stress if you don't have that memorized. But yeah, I hope this helps.